Greetings once again, 8th graders. Today I want to talk to you about the complex plane. So the complex plane is going to be, it's going to look a lot like what you've called a Cartesian coordinate plane, where it has that L1 and L2 axis. As we'll indicate right here, sure. Except now that L1 axis will have in the x-axis, that's going to be for the real numbers, and the L2 axis will be for your imaginary numbers. So where z is some element of the set of complex numbers, and z can be written as a plus bi, right? Okay, which is what I'm going to say here. So let's say point P is our z. Let's say our number is 5 halves plus 3 over 2i. Again, this is a nice little candidate for our to call z. And I say this because on exercise 309 you're saying, okay, let's say you have some complex number z. Fine, let's just say this is the z. All right, kids? So one thing that you're going to see, hopefully you see this anyway, this point down here, this is going to be the plot of z bar. That is to say, the conjugate of 5 halves plus 3 halves I. If I ask you what's the conjugate of 5 halves plus 3 halves I, hopefully you would automatically say without much thought, 5 halves minus 3 halves I. See, the only difference there is the change in the sign in the middle. If I asked you for the opposite of z, that's going to be the plot of a over here. And that's going to be where I flipped both sides. I've got negative 5 halves minus 3 over 2i, just like so. And then, of course, the only thing left here for z is to be the opposite of z bar, of course, like so. And this would simply be negative 5 halves plus 3 over 2i. See? Again, yeah, these labels right here are all with respect to z. Obviously, if z happens to be down here, now everything's going to change. Keep all this in mind, of course, as you go to complete exercise 309 and answer the questions about the midpoints. And if you struggle, it's on the notes as well. So exercise 310 is a proof that's filled in, but it's an interesting thing that happens with this, and that is that on exercise 310, you're told about this. You get a parallelogram here. If I take any two complex numbers that are plotted on the Argand diagram, let's say a and b are representing complex numbers, their sum would be represented by c, and if I connected those 3 points with the origin, I'm always going to wind up with a parallelogram. It's kind of a neat thing here. So, for instance, let's say that on this particular diagram here, I've got negative 3 minus I for B. And then up here on A, I'll have, let's call that 2 plus 3I. Yeah, it looks appropriate, I think. So, what are the coordinates of C? Well, we'll see. If I just told you that C was the sum of A and B, well, negative 3 plus 2 is going to be negative 1, and yeah, it does kind of line up with the negative 1 right there. And wait, there's more. Negative I plus 3I is going to be plus 2I, and yeah, it is positive 2. It's lined up with 2 notches up on the vertical axis there. Awesome. So when I go to find the slope on an Argand diagram like this, now you may recall how slope works on XY axes. In this case, it's not XY axis so much as it's A and B values here. That is, if I take let's take the slope of CB here. For points between those, as you can see. Well, actually, we could cheat and see it right down here. The run from B to C is A. Yeah. So segment CB is what I'm trying to say here. Yeah. The run is that's the bottom numbers there. So that is to say, when I'm looking at the run, that's negative 3 minus negative 1. What is that? Looks like looks like 2 units. And well, I mean, I wrote -3 minus -1, and really that's I mean, I say 2, but obviously, well, you know what? And I said CB, and I said CB, and I wrote it as BC. The point being is that if I say, I mean, okay, I can write it like this, it's fine. So now when I'm taking the imaginary values, if I take, let's go -I minus +2i, now I've got -3i, which of course I can simplify to 3i over 2. Okay, so what I was wanting you to see on this though, you know, the slope of this, notice its relationship to those values here on A. See? And that's not an accident. So that's the yeah, that's like I said, they kind of formalized that in the proof. That's what all this is going through here, and they you know have to have the nice, you know, if you're going to have this general statement, you have to cover all the specific cases where A is 0, where A is not 0. In any case, you'll see that it'll always come out to be a nice parallelogram. It's pretty cool. All right, but moving on down here, exercise 311, you can, you know, just fill in these proofs again. Yeah, it's just more work with the Argand diagram and how these slopes are working. I'm not going to test you over that too terribly much. I mean, for now, just understand that how the slopes relate to, you know, it looks the exact same way you did on the XY coordinate plane. That's all you have to keep track of, folks. So let's move ahead here. We'll go to exercise 312. And on this one, this is just a proof saying every non-zero real is the square of exactly 2 complex numbers. And it sounds, and here's the proof of it again, you know, it sounds complicated, but really, if you just boil it down to this, if you say, you know, every non-zero real is the square of exactly 2 complex numbers, how can that possibly be? Well, here, this kind of works like this. I mean, so they give you the 2 cases here where the r is greater than 0 and where r is less than 0. The greater than 0 you already knew, but the r is less than 0, that might weird you out a little bit, which is to say, if I was going to show this, if I had some complex number equivalent to some negative number, so like if I say -7, you know, just to be easy here. Yeah, so what's z? Well, we could solve this by adding 7 to both sides, and I've got z squared plus 7 equals 0. Now, of course, there's no real solution for this. However, there is an imaginary one, because I can use what I know about sum and difference. But now, of course, you said, wait a minute, that's not a minus. But now that we have I available to us, I can write I root 7 on both of these. Pretty clever, huh? So that is to say that z is going to be negative I root 7, or z is equal to positive I root 7. And, you know, behold, a complex number where the real number portion is 0 and the b part is, well, square root of 7. But nevertheless, that's what they're saying here on this proof of, you know, on 312. The reason you're made to look at that is because I want you to understand that you can complete the square on any quadratic equation, even where the discriminant is a negative value. So that is, and they you know, will walk you through right here on this how we can solve this as, you know, we're using completing the square techniques, right? Because, you know, using the difference of that difference of squares factorization, I get z plus 1/2 squared, and I say minus 1/2 quantity squared. And yeah, I mean, again, you can see where they're, you know, coming from here. We have you know, exactly 2 complex numbers, so that's square root of 3/4, namely I root 3/4 and negative I root 3/4, and which simplifies as so. And thus you've got z equals negative 1/2 plus or minus I root 3/2. Now, again, you know, so we're showing you this, that, hey, look, you can solve this using completing the square. And that's really, really good. I want my A students to do that. But the truth is, everybody can solve these quadratic equations such as these when they're, even when they're complex numbers, simply by using the extended quadratic formula. The proof for that is on exercise 314. Just fill in the blanks on that. It's easy enough. But basically, yeah, it's the quadratic formula again, where h is representing the discriminant, right? So h squared is, b squared minus 4ac. So yeah, that's how we'll do it. So, which is to say, if you can remember that quadratic formula again, it's not going anywhere. This will work. Negative b plus or minus the square root of b squared minus 4ac. And again, the fact that I'm able to extend this over complex numbers just tells us that b squared minus 4ac can be a negative number. That's all. So, yeah, when you go to solve a problem, say like C, where a is 1, b is 2, and c is 3/2. Yeah, I mean, we can actually, we can solve this. No problem at all. It's just you just have to substitute appropriately here. Let's go ahead and try it. X equals, and I have, let's see what I've got here. I've got negative b, I said, so that's going to be negative 2. Plus or minus, and then I've got 2 squared, which is 4, and then minus 4 times, well, let's see, a is 1, and c was 3/2. That's fine. And that's all over, 2 times 1, or simply 2. And when I take 4 times 1 times 3/2, that's, what is that, 6 minus 6? So I got 4 minus 6. So I wind up with negative 2 plus or minus the square root of negative 2 all over 2. This will, of course, simplify, because when I have this, I have negative 2 over 2. This pretty clearly is negative 1. And then I've got that root of negative 2 over 2, like this. So now on this one, when I went to load the model answer for this one, you may notice that it actually says 1 over the square root of 2. And, then it has the I, of course. Whereas on this, when I finish this, you may notice I have, my I root 2 over, 2. What I want you to understand here is root 2 over 2 is equivalent to 1 over root 2. It's just, one's simplified. EMF is fine if you solve this by completing the square and you left it as 1 over root 2. Indeed, it shouldn't penalize you for rationalizing your denominator, but that's where you have those answers in there. All right, so that's going to do it for today. Just go ahead and make sure you're completed through exercise 314. On those IXL, they're the pre-calc R skills, I would like for you to be all the way done R2 through R6, and yeah, that's what I'd like you to have done by the time I get back, and hopefully I will see you very, very soon. Have a great rest of your day, and be good for the sub, please. Thank you. Bye.